Our first speaker is Abdurrahman, who is a fourth-year PhD student at Purdue University, advised by Professor Sanjay Rao. His research focuses on network resource allocation, considering data uncertainty, and solving it using artificial intelligence. And he's looking for internships, so please feel free to reach out to him after the session.
Thank you, sir. Hello, everyone. I'm Abdurrahman, and today I'll be presenting our work, solving multi-class TE using neural models. This work is done by researchers from Purdue University and Meta. Traffic size is increasing very quickly. Prior work has reported 100 times increment in the size of traffic, in the size of one traffic just in the recent years. And they also reported that performance requirements or service level objectives are getting more and more stringent, where bandwidth should be guaranteed 2 nines to 4 nines of the time, depending on the type of the traffic. So to handle these phenomena, network operators would categorize their traffic into multiple classes and assign them different priorities to better manage SLOs or service level objectives for diverse traffic. For example, web search will be assigned a high priority since it's a delay-sensitive traffic, but data replication across data centers will be assigned a lower priority since it's not a delay-sensitive traffic. So how ones are managed today? Management of one traffic, or traffic engineering, starts by taking as inputs a set of traffic matrices, a set of capacities, and a set of predefined tunnels, which all are fed to a centralized SDN controller that has a global view of the network, optimizes a network-wide objective, something like maximize carried flow or maximize fulfillment ratio, where it employs linear programming to route traffic. However, one issue with this pipeline is the resiliency to demand prediction error, which impacts the ability to meet SLOs. And to show why this is problematic, let's consider this simple 2 nodes example, where the predicted demand for 2 traffic classes is 1. And let's assume link capacities are also equal to 1. An optimal routing for this setup is to send all high traffic on the upper link and all low traffic on the lower link. However, it turns out that actual high-class traffic is beta more than predicted, and actual low-class traffic is beta less than predicted. And when we apply this routing over the actual demands, it sends 1 plus beta of high traffic on the upper link and 1 minus beta of low-class traffic on the lower link, causing beta loss of high-class traffic, though the network can carry all traffic. And what we conclude out of this simple example is that what is optimal for predicted demand may not perform well on actual demand. That said, there has been a shift in the recent years to apply neural models instead of linear programming solvers. And this is mainly because they are resilient to demand prediction error, which results in a better routing. To justify the need for our system, Hattrick, let's take a look on the current state of the art, where on one axis, we have the ability to support multiple classes, and on the orthogonal axis, we have the resiliency to demand prediction error. State-of-the-art methods can be categorized into 2 groups. The first one can support multiple classes, but it is less resilient to demand prediction error. Examples of these are SWAN, EBB, B4, and Flexile, which all are linear programming-based systems. The second group of systems is more resilient to demand prediction error, but it only supports a single class of traffic. And examples of these are HARP and DOT, which are machine learning-based TE. And then comes our system, Hattrick, that can support multiple traffic classes and being resilient to demand prediction error. Furthermore, Hattrick differs from state-of-the-art methods on another dimension, which is the ability to optimize metrics generated or given by a simulator. All the previous state-of-the-art methods regardless, linear programming-based or machine learning-based, are model-based methods. That is, they only optimize metrics defined by the optimization model. Hattrick is the first step towards optimizing metrics generated by a simulator. In this context, the simulator models network behavior under congestion due to demand prediction error. For example, traffic prioritization at routers. Optimizing metrics generated by a simulator is a unique, untapped opportunity available to machine learning-based techniques. Our contributions in this work is the Hattrick system itself, which is the first machine learning-based TE scheme that can handle multi-class TE. In terms of performance, Hattrick outperforms state-of-the-art multi-class TE scheme, where it improves the 99th successfully delivered flow relative to Microsoft SysOne by 5.5% to 19.3% across traffic classes. Improvements are up to 11% relative to an optimal linear programming-based strategy. Hattrick also reduces computation times, where it can be 280 times faster than the optimal LP-based strategy, and it can be up to 36 times faster than SWAN. To motivate the design of Hattrick, let's first have a tour over the challenges of designing an efficient machine learning-based multi-class TE. The first challenge is the ability to handle multi-class TE. And the second challenge is to respect the priorities of different traffic classes. While the last challenge is the ability to handle demand prediction error. We addressed the first challenge by having a neural architecture that is aligned to optimization techniques of multi-class TE, and tackled the second challenge through precedence-aware learning. As for the last challenge, we handled it by learning with feedback from a simulator and by introducing auxiliary metrics. Before taking a look on Hattrick's architecture, I note that I will explain it assuming 2 classes of traffic, but the paper shows 4 more. Hattrick starts by feeding a predicted high-class traffic matrix to its first stage of optimization, which generates an initial routing for the high-class traffic. Then, this initial routing, alongside 2 predicted matrices for 2 traffic classes, are fed to a second stage of optimization that spits out fine-tuned final routing for high-class traffic, and it also generates final routing for low-class traffic. I highlight that the second stage of optimization of Hattrick can tune high-class routing to jointly optimize both classes of traffic, which aligns the architecture to the optimal linear programming-based strategy. Please refer to the paper for much more details about the architecture. After getting the final routings, one obvious thing to do is to apply them directly in the network over the actual traffic matrices, which will generate an effective carried flow for high-class traffic and effective carried flow for the low-class traffic. And I say effective because of the demand prediction error, which might cause packet drop and overutilization of some links. But furthermore, we know that one router's scheduling policies prioritize higher class traffic. So we would expect the network to carry more of the high-class traffic and less of the low-class traffic. So we opt to capture this with a simulator and then optimize these effective carried flows generated by the simulator with Hattrick. Such simulated metrics are not considered by existing techniques. To see why this is helpful, let's look at this example, where using the simulated metrics, Hattrick can learn to mix traffic. And to see why this is helpful, why mixing traffic is helpful, let's consider this simple example, where the routing based on predicted demand might say, send all high traffic on the upper link and all low traffic on the lower link. But then we simulate this on actual traffic. And it turns out that high traffic is more than expected. And in this case, the network will drop high-class traffic, unfortunately, which is the most important traffic. But a different routing will actually mix traffic classes over both links. And when this is simulated using actual traffic, where high class is still more than expected, the network will start dropping low-class traffic and isolate high-class traffic to the best it can. This shows the benefits of using simulated metrics. The second component of tackling prediction error is introducing auxiliary metrics. And this is mainly because networks are well provisioned for high-class traffic, which means these are easy to route and optimize, which means that gradients for high class vanish very, very quickly, which yields a limited training and brittle models. So to solve this, we minimize the maximum link utilization and maximize the effective carried flow for each class. And there are more details in the paper about this. But then an interesting question to ask is how to handle this hierarchy of metrics, where some metrics are more important than others. And this takes us to the last piece of Hattrick, which is a precedence-aware learning. And to explain a precedence-aware learning, let's look at this simple example where we have two gradients, GH and GL, corresponding to two traffic classes. In this case, GH and GL are conflicting. And to handle this, we decompose GL into two components, one orthogonal to GH and one parallel to GH. And we always remove the parallel component, and we only use the orthogonal component to update Hattrick parameters. We note that in this example, not removing the parallel component will counter-optimize GH, in fact, yielding these final gradients. This is our adaptation of machine learning techniques for hierarchy of metrics. For the experimental setup, we used 4 datasets. Private one, which is the data collected from a real Cloud WAN that natively support 3 traffic classes. Giant, which is a public dataset, which we split into 3 traffic classes using private WAN traffic ratios. And then we used KDL and US carrier with synthetic traffic matrices. For the baselines, we compared Hattrick to BestMC, which is an optimal LP-based strategy, to Microsoft Swan, and to DOT and HARP, which are machine learning-based TE schemes. And in all of our experiments, we used the 3 traffic classes. We start by comparing Hattrick to linear programming-based methods using the Giant dataset. For the high-class traffic, and let me define first the metric. We used or defined the normalized fulfillment ratio metric, which is the carried traffic of class C using a scheme divided by the carried traffic of class C using an oracle or clairvoyant BestMC. For the high-class traffic, we see that Hattrick outperforms both of BestMC and Swan. I note that BestMC is suboptimal due to prediction error, but it's optimal if it's given accurate predictions. I also emphasize that for the highest class traffic, the normalized fulfillment ratio is always less than or equal to 1. Staying on the same comparison, but for lower classes, mid and low class, we see higher wins and clearer wins for Hattrick over BestMC and Swan. And also, as expected, normalized fulfillment ratio for lower classes can be and is greater than 1, which indicates a priority inversion, which means the system has served more of a less important traffic at the expense of a more important traffic. And there is a concrete example about how this can happen in our paper, so please refer to it if you are interested to know more. We then compare Hattrick to other machine learning-based TE schemes extended to multi-class TE. We compare Hattrick to HARP MC on the mid and low classes of traffic. And we see that Hattrick achieves a significant win over Hattrick. And in the paper, we show that Hattrick also achieves a significant win over DOT. So please refer to it if you want to know more or if you want to see the results versus DOT. After that, we show the computation times for Hattrick, BIST-MC, and SWAN. On the KDL topology, which has 754 nodes and 1790 links, Hattrick is 280 times faster than BIST-MC and 36 times faster than SWAN. And in the paper, we show that Hattrick achieves a higher normalized fulfillment ratio than both of these systems. The paper also has other experiments where we show Hattrick outperforms other methods on other datasets and using different demand predictors. We also show the benefits of Hattrick's design elements. We show that the neural architecture, when aligned to the multi-class TE optimization techniques, helps Hattrick to perform better. And we show that integrating the simulated metrics helps Hattrick to carry more traffic. We also show that precedence-aware learning outperforms weighted additive loss. So to summarize, I presented Hattrick, the first neural TE scheme that can handle multi-class TE. Hattrick's architecture is aligned to multi-class TE optimization models. Hattrick is resilient to demand prediction error. We proposed a new precedence-aware multitask learning method tailored for multi-class TE specifically and hierarchical metrics generally. We integrated a differentiable simulator into the training process of Hattrick to cope with the prediction errors. Hattrick outperforms the state-of-the-art multi-class TE schemes, and it reduces computation times. We released Hattrick's source code and made it public. By this, I reached the end of my talk. Thank you for listening, and I'm happy to take your questions.
We have time for a few quick questions.
So Behnaz Arzani from Microsoft. So you compared to SWAN. I'm curious, since SWAN is a multi-objective optimizer, so it considers things like max-min fairness as well as the number of fib entries that it has on the switches. So did you only compare against MLU, or did you also compare against all these other metrics that SWAN optimizes over? Thank you.
Thank you, Behnaz. We just considered the maximum carried flow in the network. Yeah, does this answer your question? Okay.
Okay. Any other questions? All right, well, while people are thinking about the questions, can you elaborate a little bit on the granularity of your control, right? If the unexpected traffic is a burst of traffic, can your system handle that?
I'm sorry, what?
The granularity of the control, right? If I'm getting a burst of traffic in a short interval.
I think usually things in TE are more coarse-grained, and I think, as far as I know about your background, is more in intra-DC, where things are fine-grained, right? In TE, things are coarse-grained, where we think about traffic matrices instead of packets and bursts and this stuff.
Okay.
So.
Siva Kakalla from Microsoft. MaxFlow is a perfect LP, and in your slides you mentioned you considered other metrics. So can your framework handle MLU, max-min fairness, and other nonlinear objectives?
I'm sorry, can you please repeat?
So from what you mentioned for the previous answer to Behnaz, you said MaxFlow, which is a perfect LP problem. Mm-hmm. But can your framework handle other metrics, as your slide said, like MLU, max-min fairness, and other nonlinear ones?
Max-min fairness we did not tackle, but for maximum link utilization, it can. In fact, maximum link utilization, as I mentioned, it's part of the optimization in Hattrick. And this is mainly because we, in some sense, we do not view maximum link utilization to be orthogonal to MaxFlow, which I believe to be the case in all previous TE work. These are not orthogonal things. In fact, the optimal for MLU, when MLU is less than 1, is an optimal for MaxFlow. And we exploited that in some sense.
And even in a single class, okay.
We have to move on to the next talk. Let's continue this offline. Let's thank our speaker again.